I'd like to give you a brief introduction to the notion of antiderivatives. So now we are in the last chapter in this course. And the idea is fairly simple. It's just derivative in reverse. So if I said that f of x is x squared, then you know that you can compute using the power rule that f prime of x is 2x. So 2x, f prime of x equals 2x, is the derivative of x squared. Another way of saying that is that x squared is an antiderivative of 2x. So if you can sort of think of this as the Jeopardy version of derivatives, where I'll tell you the answer and you figure out what the question was. So if f of x equals 2x, let's say f prime of x was 2x, what was f of x originally? Well, f of x was equal to x squared. This is the antiderivative of that. Now, right away, that brings a question. Is this the only function, is this the only antiderivative of the function 2x? Is this the only thing I can take the derivative of to get that? I want you to think about that for a second. Pause the video, ask yourself the question. Presumably you've paused the video and asked yourself the question. And the answer is no. There's more than one function I can take the derivative of to get that. I could also have taken the derivative of x squared plus 1. When you take the derivative of the 1, you just get 0. The derivative of x squared is 2x. I could also have taken the derivative of x squared minus 30. I could have added or subtracted any constant to x squared and I still would have gotten 2x. So the general antiderivative of 2x is x squared plus any old constant. Now you have to ask yourself, is that all? It turns out that it is. That's every antiderivative of 2x is this. The only way you can get 2x as the derivative is start with that. We're not going to go ahead and try to prove that right now. I want to give you a notation for antiderivatives. So if I put 2x inside, in between these two symbols, the first one being the sort of vertically elongated s, and the second one being dx, that differential that we just talked about from the previous section. Just think of this right now as all one symbol. Think of this as like open quotes, and this is closed quotes. And this thing inside is what you want to take the antiderivative of. Well, we're looking for a function whose derivative is 2x, and that could be x squared plus any old number. So the antiderivative of 2x is x squared plus any old number. Hopefully that makes sense. Let's compute a few more antiderivatives. So right now, we're just sort of flying by the seat of our pants. We know how to take derivatives in the forward direction. Now I'm just asking you to sort of look through your memory and peek over your shoulder and see if you can figure out how to do it in the reverse order. Let's say I ask you, what is the antiderivative of 3x squared? In other words, somebody just took a derivative and that was the answer. What was the question? Pause the video and think about it for a moment. See if you can write down an answer. Well, the thing that they took the derivative of to get 3x squared was x cubed, possibly plus a constant. So if you take the derivative of x cubed, the 3 comes down, we write the x, the 3 becomes a 2, 3 minus 1 is 2, and the c goes away entirely. So the antiderivative of 3x squared is x cubed plus a constant. The general antiderivative of 3x squared is x cubed plus a constant. Again, think of this as open quotes and closed quotes, and what you're supposed to do is take the antiderivative of the thing inside. Let's try this. What did somebody take the derivative of to get cosine of x? Again, pause the video. See if you can answer the question. Well, they took the derivative of sine of x. If you take the derivative of sine of x, you get cosine of x. If you take the derivative of c, of course, you get 0. Let's do another one. What does somebody take the derivative of to get e to the x? Again, pause the video. Well, you take the derivative of e to the x plus possibly a constant. You're going to have to put in the plus c every time you're taking these antiderivatives. Let's do another one. I'm going to keep this one on the blackboard, and I want you to see if you can figure out what the antiderivative of x is. You know the antiderivative of 2x is x squared plus a constant. What's the antiderivative of half of 2x? Pause the video, think it over. Well, it's just x squared over 2. Or you could just as easily have written this as 1/2 x squared. If you take the derivative of 1/2 x squared, the 2 comes down and multiplies the 1/2, they cancel. The 2 becomes a 1, you just end up with x, the c goes away entirely. Here's a memory test. What about secant squared of x? What was it that we took the derivative of to get secant squared? That should look familiar. It's hard to do these things in reverse. Well, we took the derivative of tangent of x. Derivative of tangent is secant squared. We worked that out using the quotient rule. And one more. What's the antiderivative of 1 over x? Or we could have just as easily written 1 over x as x to the minus 1. There was something we took the derivative of to get 1 over x. What was it? If you said the natural log of x, you're right. So again, from this, what I want you to take is this notation and the idea of an antiderivative, and the fact that when you take the general antiderivative, you have to put in the plus c every single time.